let us do the calculations for the first exercise. Now the TMA and the AMA and the mu sub k, we're going to do each one separately. So this is the equation we're going to use to find mu sub k, but to find the efficiency, we have to find the AMA, the actual mechanical advantage, and the TMA, the theoretical mechanical advantage. Now, for the first set of measurements, we had the mass of the block being 209.8. So 209.8. And that gives you a weight in newtons that corresponds to 2.056 newtons. Now, how did I find that out? Take 0.2098 and multiply 9.8. Now, the mass on the hanger, if you remember, was 125.2. So 125.2. So what does that correspond to? What weight does that? Is 0.1252 times 9.8. So that's 1.227. Now, from those, we get the actual mechanical advantage. It's actual because it's the actual amount of mass we had to put on to pull the thing up the ramp. So what you do is you get the ratio of that, 2.056 divided by 1.227. And the actual mechanical advantage that we got is 1.676. So again, you're going to have to do this the other two times. I'm going to do this just for one of your data sets, and you're going to repeat this for the other two angles. This is for the first angle. Find the actual mechanical advantage. You also could have taken 209.8 divided by 125.2 as well, because 9.8 is in both of these, and you take you divide one by the other, 9.8 cancels out. Now, for theoretical mechanical advantage, you look at the distances. So the height of that particular case was 23.3 centimeters, and the length was 80.9 centimeters, correct? Now, the theoretical mechanical advantage, that's L divided by H. So you don't really have to convert to meters unless you want to, because the centimeters cancel out. So what you do is you take 80.9 divide by 23.3. You get a theoretical mechanical advantage of 3.472. That's, both of them are unitless, the AMA and the TMA. So we've got the TMA being 3.472 and the AMA. Now, what does that mean? It means that this is the best you can get. Remember, work equals force times distance. What you're doing is you're increasing the distance and decreasing the force necessary to pull it up a ramp. Now, the amount of force less that you need going up a ramp is a mechanical advantage. Theoretically, you could get 3.4 times less. You could push with 3.4 times less the amount of force to get it to go at this angle. However, in reality, you only get an actual mechanical advantage of about 1.7. So in other words, you push 1.7 times less than you would if you pulled it right up. So you do get some sort of mechanical advantage. It's not as much as the theoretical. And that's because there's a lot of energy being wasted in the form of friction. All right, friction. Again, the friction will depend on the angle. The lower the angle, the more friction you get. But the frictional coefficient is going to remain the same. However, the frictional force will change depending on the angle. So now, what's the efficiency? The efficiency is always the actual divided by the theoretical. Sorry about the extra noise. They're moving somebody outside into another classroom space. Usually during the summertime, nobody's around, especially with this COVID, but today it just happens to be a little noisy. So 1.676 divided by 3.472. That'll give you the efficiency. So I get 0.483. Now that's corresponds to 48.3% efficiency. In other words, about 50% of the energy is being wasted in the form of friction. So It's because you're wood on wood. If you had wheels underneath there, the efficiency would be much, much higher. Now, our last calculation has to deal with the mu, to find the coefficient of friction. So what we're going to do is, I'm going to just rewrite this up here, down here, so. And remember, you're going to do the AMA and the TMA and the efficiency the same way for the other two data sets. So what I'm going to do is I'm going to multiply both sides by, multiply and divide. So I'm going to get, this becomes 1 plus mu k cotangent theta is equal to 1 over efficiency. Oops, I'm running out of space, okay? Then all I have to do is subtract 1 from both sides. I'm doing just a little bit of algebra. So I have mu k cotangent theta is equal to 1 over efficiency minus 1. Then to get mu sub k all by itself, I just divide both sides by cotangent of theta. This over 1 tangent efficiency minus 1, and divide the entire thing by cotangent of theta. Now what we can do is start plugging in data. I know what the efficiency is. Oh, wait a minute. I don't know what the angle is. And what is the thing with cotangent? All right, so cotangent, for those of you, is 1 over tangent of theta. So we can actually rewrite this as 1 over efficiency minus 1 times tangent of theta. All we have to do is find theta. All right, to find theta, well, we know what the length is. The length is, let's see, 80.9, right? And the height is 23.3. So if you look at a little diagram here, we've got the length and the height. That's opposite over hypotenuse. That sounds like sine. So sine of theta is opposite 23.3 divided by 80.9. So we can find the angle. The angle is inverse sine of 23.3 divided by 80.9. So take 23.3 divided by 80.9, then take the inverse sine of that, and you will get an angle of 16.7 degrees. So now let's find mu, and again, the mu should remain remarkably the same for all three. Even though the angle's the same, the mu is the same because the two surfaces are the same. So 1 over the efficiency, 1 over 0.483 minus 1, times tangent of 16.7 degrees. Now, I also could have measured the horizontal distance. I just decided to, we might as well remind ourselves of trig. So go ahead and calculate that out. Tangent is 60.7, and then multiply that by whatever inside of here, and you'll get mu sub k. Now, remember, for wood on wood, it's between 0.25 and 0.4. That should, be the range of values for the actual, or the coefficient of friction. Okay, so if it's between 0.2 and well, it depends on the wood, maybe up to 0.5, but usually it's between 0.2 and 0.4. That's usually, somewhere in between there would be the coefficient of friction for wood on wood. Okay, so just do the other two angles the same as this one.